Alright, so the first thing it shows us here, these two rectangles, and it says that both of these rectangles have an area of 144 square units. Sketch as many other rectangles as you can that have the same area. Well, instead of actually sketching the rectangles, are y'all cool with me just writing out the dimensions, the length and the width? Alright, so let's start. If we had a length of 1, what would my width need to be for it to be 144 square units? Because remember, area equals length times width, correct? So if my length was 1, what would my width need to be for it to be 144 square units? 144. Alright, we were already given 2 and 72, right? Y'all see that up here? That was given to us. Does 3 go into 144? Yep, it does. 3 times 48. So if we had a length of 3, we could have a width of 48. We'll see if 4 goes into 144, and it does. 4 times 36. It's 144. But I know 5 doesn't go into 144. Does 6 go into 144? Yep, it was actually one of those that we were given. It was that second one. Does 7 go into 144? 8? Alright, 8 times 18. Does 9 go into 144? Ten doesn't. I don't think 11 does. 144 divided by 11 is 13. No, 13 and some decimals. But then we all know 12 times 12 is 144, right? Alright, so now we say, it says considering the rectangles with an area of 144, what happens to the width of the rectangle as the length increases? So if this is length and this is width, as our length is increasing, what's happening to our width? It's decreasing, yep. So as length increases, width decreases. Alright, so let's kind of examine what's going on here. So if I go from 2 to 4, so I'm doubling my length, right? What happens to my width? It goes down by how much? If I double my length, what's happening to my width? My width gets cut in half, doesn't it? The 72 divided by 36, is that cut in half? Yeah. So if I go from 6 to 12, I'm doubling my width. My length, correct? 12 or 24 divided by 12 would be 2, right? So I'd be cutting it in half again. Let's see. If I triple my length, am I dividing 48 by 3? 48 divided by 3 would give me 16. So, examine at least 5 other pairs of rectangles, each pair sharing the same area. How would you describe the relationship between the lengths and widths? So, in each pair, the lengths and widths are different by reciprocal factors. So when we doubled our length, we cut our width in half. If I tripled my length, I cut it by a third, okay? That's what I mean by a reciprocal factor. If you even wanted to write that way, if you look back, double length equals width cut in half. Everybody got this page? Alright, now they want us to determine the inverse variation of each table. Well, we hadn't really talked about what inverse variation is, but I'm going to come over here and I'm going to draw a table that's given to you in your book. We got X and Y. So we got 1 and 12, 2 and 6, 3 and 4, 4 and 3, 6 and 2, 12 and 3. Alright, I'm not just making these up. I'll show you in the book where this came from. Maybe. Well, I said I was going to show you. Let's see if they'll let me show you this way. Alright, so here's our table right here. Y'all see that we just wrote? It says an inverse variation is a relation between the two variables such that as one variable increases and the other decreases proportionately. So our x values are increasing and they're saying that it should decrease proportionally. For that table to represent an inverse variation, the product, so what's it mean when you get a product? What are we doing? Multiplying. So the product, so x times y, must be constant. So that means it must be the same. Find the product xy for each column in the table. So this is to determine whether or not these values represent an inverse variation. So what's 1 times 12? 12. 2 times 6? 12. And what we want to do is we want to make sure they're all 12. 3 times 4 is 12. 4 times 3 is 12. 6 times 2 is 12. And 12 times 1 is 12. So because it is constant, because it is the same throughout each value, each x value times its y value, they say it does represent an inverse variation. So I wrote, yes, constant of variation is 12. All right, the second table they gave us in this example was 1 and 20, 2 and 17, 3 and 14, 4 and 11, 5 and 8, 6 and 5. All right, so let's multiply these together to determine whether or not this is an inverse variation. What is 1 times 20? Is what? 20. 2 times 17? 34. So automatically, what can I tell? Is this an inverse variation? No. So I wrote no, there is no constant of variation. All right, so let's look at these two tables they give us. 1 times 25.5 is going to be 25.5, right? Can somebody multiply the next few for me? Do what? All right. 25.5. Next. All right. This is 25.5, right? And what's the next one? It's also 25.5, right? So, does this table represent?
Orange Day, second lunch. Grab and go. Report to the cafeteria.
Does it represent an inverse variation? Yes. Our constant of variation is 25.5. Alright, so we were just looking at constant variation where we take x, we multiply it by y. So we're going to do the same thing here for b. So I take 6.6 times 3, and I get 19.8. 5.5 times 5, I get 27.5. So is there truly any reason for me to keep going? No. So I'm going to write no, there is no constant of variation. Alright, now they want us to actually write an equation for our inverse variation, just given an x and a y value. But they tell you what those equations are, so they make it a bit easy for us. They give us 3 separate equations, and those 3 equations are y is equal to k over x is equal to k over y, or x times y is equal to k. So I'm going to write all those. Y is equal to k over x, or x is equal to k over y, or x times y equals k, where k equals our constant of variation. So right here they give us x and y. They tell us x equals 6 and y equals 1/2. So what that means is we got to figure out what k equals, right? K equals x times y. Well, do we have both of those? Yep. 6 times 1/2. So that means k equals 3. Now they just want us to write an equation that represents that, and that would be y is equal to 3 over x. What is the value of y? Using this inverse variation when x is equal to 15. So we put 3 over 15, which simplifies to 1 over 5. So y is equal to 1 over 5. We got it? All right. The amount of time it takes for an ice cube to melt varies inversely to the air temperature. So time equals K, we don't know what K is, over air temp, right? At 70 degrees, the ice will melt in 20 minutes. So at 70 degrees, we know the air temp, right? And we know our time. So there we can figure out K, correct? So at 70 degrees, oh, I did that backwards. What should that have been? 20. At 20 minutes, our ice cube will melt if it is 70 degrees outside. Well, how do I get K by itself? Can I cross multiply? 1400 equals K, right? So how long will it take for the ice to melt in 85 degrees? So now we know our equation, though, is y is equal to 1400 over x, right? Well, how long is it going to take to melt in 85 degrees? So what did we say? Y was our time and our air temp was x. So y is equal to 1400 over 85. So y is equal to 16 point, can somebody help me out? What? 0.47 minutes, right? All right, graph the function and what are the domain and range and asymptotes of the function. That's probably a new word that you have yet to hear of. So we're going to come over here and we're going to make ourselves a table. It's going to go from -5 to +5. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. And I'm going to go here to alpha y equals and put 10 over x. Do what? Can I show the graph? Oh, the table. Okay. Alright, so at -5, my y value is -2, correct? I'm just going to go through and put my whole numbers for now, just because it's a little bit easier. We'll go back and do the decimals here shortly. Claudia, do you have the table pulled up on your calculator? Okay, I'm going to take mine down. At 4, what's the fraction you have? Is it -5 over 2? Positive? At 4? Oh. Yeah, I meant -4. Sorry. Alright, so I'm going to write it as a decimal because to me, graphing, when I see a decimal, that's a little bit easier than trying to figure out what the fraction is. Would y'all agree? Okay, so at 3, is it -3.3 repeating? Negative what? -10 over 3, which is -3.3 repeating. Okay. And 0, I think it tells you an error message, doesn't it? What that means is it is undefined there at 0. Okay? And then at +3, it's going to be a positive 10 over 3, right? Which is a positive 3.3 repeating. +4 is 5 over 2, which is 2.5. If you can't see that, that should be 2.5, okay? So I'm going to just draw my lines here in the middle. On my y-axis, I'm going to go up by 2. So 2, 4, 6, 8, 10. I'm going to do the same in the bottom. -2, -4, -6, -8, -10. And then we'll just go by ones on our x-axis, okay? Alright, so I'm going to plot the points I have. 1, 2, 3, 4, 5, down 2, which, alright, negative 4, negative 2.5, negative 3, negative 3.3, negative 2, 2, 4, 5, and 1, negative 10. Alright, I'm going to graph these others on the other side of the 0 right there. So it tells me at 1, I've got 10, 2, 5, 3, 3.3, 4, 2.5, and 5, 2. Alright, so I want you to be very careful when drawing these, that you do not go past the x-axis or the y-axis, and I'll explain why here in a minute. But if you were to put this in your calculator and see the shape of this graph, it would look something like this. And this is what they call a reciprocal function. In a reciprocal function, the domain and range are always all real numbers, except x cannot equal something, and all real numbers and y cannot equal something. Well, how do I know what x and y cannot equal? That's going to come from your vertical asymptote and your horizontal asymptote. Well, how do I know what my vertical and horizontal asymptote are? What even is an asymptote? That is a, let me give you the actual definition, and I kind of ad-libbed a little bit of it in the last class I had. But that tells us, well, there's been several pages in the book, I didn't realize. Alright, there's our definition that we need. It says an asymptote is a line that a graph approaches. So yes, it's a line that a graph approaches, but it never touches. So this is our graph, right? 10 over x. Let's go back to home. And that's what yours looks like, correct? But did y'all notice over here, you see how it looks like it's getting mighty close to this x-axis? And even if alright, so if I am to zoom out, it actually looks like it's on the x-axis, doesn't it? But look, if I zoom in, do you see how it gets super close to it, but it's never actually going to touch it? So an asymptote is a line that a graph approaches but never touches. So in this case, we are undefined at x equals 0. Do y'all see that? We are undefined at x equals 0. So that means x cannot equal 0. Well, what does that tell? What else does that tell us? That also tells me that I've got a, it's going to be kind of hard to see, but what I'm doing is I'm drawing a vertical asymptote right here. Hard to see because of my graph being black. But do you see how I drew a dashed line? So that's telling me that this graph is going to get super close to this dashed line, and that's my vertical asymptote, x equals 0. It's going to get super close to that dashed line, but it's never going to touch it. This is your x value. Your vertical asymptote is your x value. And your horizontal asymptote is going to be y is equal to something. Well, it's actually getting close to this point right here, but it's never going to touch it. And that is y is equal to 0. All right, the next graph, got y is equal to x 1 over x plus 2 minus 4. Just to kind of speed up things, I'm going to just tell you what our values are. We'll start at -7 and go to +3.
If I get one more nasty email from you about not paying my bills, okay? I'm just kidding.
I BCC it, that way nobody knew who I was in the group.
You what?
I made it where you couldn't tell who I was in the email.
Yeah,
It's not just you, I promise.
I'm trying to watch the writing, so damn it.
Jordan's watching it. Did they win yesterday?
Les said that if they go to Arlington, that he may take Bryce and go to.
Mm-hmm. Oh no, Texas.
Mm-hmm. They'll be playing in NLCS.
All right, back to what I was doing. I went ahead and gave you the table just because we're on a time crunch here. And we are undefined at -2. So that's actually going to be easy for us. That tells us what our vertical asymptote is. So we got domain, we got range, we got vertical asymptote, and I've got horizontal asymptote. So domain is all real numbers, and we know that our vertical asymptote is our x value, that is x equals -2, right? So that means our domain says all real numbers except x cannot equal -2. So you're going to be able to see it better this time. So at -2, I'm going to draw a vertical line. It's a little bit easier to see when it's not right on the axis, right? Oop, I don't mean to draw that arrow. Okay, so our range we know is all real numbers. We don't know what y equals yet, or what y cannot equal. So I'm going to plot these points. So at -7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4.2, -4.25, -4.3, -4.5, -5. This one looked a little bit different. I mean, it still looks the same, but just a tad bit different. And then we've got -1, 1, 2, 3, -3. And then we go down to -3.5, -3.6, -3.75, and -3.8. So basically, you can kind of see here that the horizontal asymptote is getting mighty close, and my line actually kind of went over it, but it should have been at right here. Do y'all see how it's getting close to this line, but it never touches it? So it should have been here at y is equal to 1, 2, 3, -4. And we're going to look more at this tomorrow, so I know this is a lot to take in for today, but we will look at more of this tomorrow.